Hey everyone, welcome back. Today's video is a complete one-shot guide to Ollama. Everything you need to know from installing it, pulling models, all the way to REST API, quantization, custom model files, streaming, and even embeddings. We are running everything live in Google Colab T4 GPU. No API key, no cost, every cell runs from top to bottom. Let's get into it. The first cell is installing the dependencies and the Python libraries to run the Ollama server. That is the LangChain, LangChain community, LangGraph, and LangChain Ollama. We use bits and bytes for transformer accelerations. Then we use ZSTD for installing the Ollama in our local machine. This cell handles all our 4 steps to install the Ollama. Step 1. We install Ollama using the official shell script. This downloads the Ollama binary and configures it on the system. This takes about 20 seconds. The step 2, we start the Ollama server as a background process using subprocess popen. We redirect stdout and stderr to debnull so that it does not flood our notebook. The server starts on port 11434 and stays running for the entire session. Step 3. We ping the server to confirm it is alive. We try up to 6 times with a 3-second gap between each attempt. You will see Ollama server is live when it is ready. And step 4, we install our Python packages, LangChain, LangChain Ollama, LangChain core. These are the only 3 we need today. As it is a time-consuming process, I ran it before and you can see the output. Setup is complete. Now let's pull our model. Cell 2 pulls that Qwen 2.57b Ollama from the model library. It is a 4.7 GB download. On a fresh Colab runtime, it takes about 3 to 5 minutes, depending on the Google's network speed. Once downloaded, it is cached for the entire session. So if you rerun this cell, it is an instant. So I have already downloaded the model. So this is the model name. This is the ID. Size is 4.7 GB, and the modified just a second ago. The output is telling us that model is ready to use. Before using LangChain, I want to show you what Ollama actually its code, a REST API. Cell 3 makes a raw HTTP post request to a localhost 11434 API generate using a Python's request library. No LangChain, no wrappers, just a plain HTTP call. The payload has 3 fields. Model is Qwen 2.57b. Prompt is our question, which is in one sentence. What is an AI agent? The stream is false, which means we want a full response at once rather than token by token. Let me run it. The model is calling API and model is giving a response. An AI agent is a computer program that acts on behalf of a user or within a system to perform tasks and make decisions based on its environment and the data it receives. The status code is 200 that is telling the server is completely okay. Total token is 35 and time token 1.24 seconds. So this is telling us that REST API is working completely perfectly. Now the chat API. Cell 4 shows the API chat endpoint for the multi-turn conversation when the model remembers the context. Instead of a single prompt string, we pass a messages array. Each messages has a role, system, user, or assistant, and content. This is the exact same format OpenAI's chat API use. We send turn 1. Asking about LangGraph, we get a response. Then we add the response to the messages to the turn 2 and asking how it is different from the LangChain. So sending the first messages, it is giving an output, and in turn 2 sending our follow-up question. Notice that the second answer reference LangGraph. It has a context from the turn 1. That is because we are sending the full conversation history with every request. Ollama is stateless. It does not remember between calls. You are responsible for maintaining the messages history and sending it each time. This is exactly how LangChain manages conversation internally. Now let's connect via LangChain. Now let's connect Ollama through LangChain, which is how we will use our agent code. ChatOllama is the LangChain connector. Look at the initialization, model, temperature, and the base URL. That's it. No API key, just point to the localhost. Compare this to Chat OpenAI. The only difference is that Chat OpenAI needs an API key, parameter set to your OpenAI API key, and the base URL defaults to OpenAI server. With ChatOllama, no key, base URL points to the localhost. Everything else is identical, the invoke call, the messages list, the response object, same interface. That's the power of LangChain's abstraction. So let me run it. You can see the output. The 3 bullet points about Ollama generated locally for free. This is what we use LLM in all our agent code. Cell 6 runs through all the key CLI commands so you have them as a visual reference. Ollama version, check what you have installed. Ollama list shows every model downloaded on the machine with the file size and last modified date. Ollama show Coin 2.57b. This is the most useful one for understanding a model. It shows the parameter count, the quantization type. You will see Q4KM here, the context length and the model family. Ollama PS shows which models are currently loaded in the memory. A model stays loaded for a few minutes after the last request before being automatically unloaded to free VRAM. The curl command hits the REST API directly and parses the JSON to show model names and sizes. And NVIDIA SMI gives us the real T4 GPU memory. You will see how much VRAM and 4.7 GB is actually using. So let me run it. You can see the output. That Ollama version is 0.18.0. Ollama list giving us the model name Qwen 2.57b. ID is this and size is 4.7 GB, which was modified 9 minutes ago. The command Ollama show Qwen 2.57b that displays the metadata about the model. The architecture is Qwen 2. Parameters is 7.6 billion. Context length is 32768. Embedding length is 3584. And the quantization is Q4KM as I told before. Ollama PS that the models is currently loaded into the GPU or CPU memory. Currently, as I am using the T4 GPU, this is loaded in the 100% GPU with the total memory size is 4.9 GB and the context length is 4096. The curl command tells us that our model is Qwen 2.7b 4.7 GB, which is in a JSON format. The NVIDIA SMI command gives the how many memories usage actually in our T4 GPU. That it is a Tesla T4 GPU which is using 4883 megabyte and 10030 megabyte is the maximum capacity. Now let's go to the quantization. This is the most important concept to understand for local LLMs, quantization. A 7 billion parameter models store each parameter as a 32-bit floating point number. That is 4 bytes per parameter. 7 billion times 4 byte equals to 28 GB. That does not fit on T4. Look at the table. Q80 8-bit integer, which is 7.2 gigabytes, fits, but it leaves also no room. But when it is come for the Q4KM, which is a 4-bit and this size is 4.7 GB, this is the sweet spot for our T4 GPU. But When we move from the 2-bit get Q2K at the 2-bit, it gets down to the 2.8 gigabyte, but quality drops to 90%. You will notice the difference in the coherence. Our actual model confirms it that architecture with the quantization is the Q4KM, and Q4KM has successfully fit with a 97% quality default in our T4 GPU. Now, the model file. This time you will build your own custom model, like building your own ChatGPT in your own hand. The model file is one of the Ollama's most powerful features, and most people skip it entirely. Think of it as a Docker file, but for LLMs. You take a base model, add your own configuration, and build a new named model on your machine. Our model file starts with from a Qwen 2.57b, our base. Then we set 4 parameters: temperature 0 for deterministic output, top P at 0.9, context windows at 8192 tokens, and max credit at 1024 tokens per response. Then the system block. This is the key part. Everything between the triple quotes is baked permanently into the model as the system prompt. Our AgentBot knows its name, its rules, and about tools and reasoning, and even where it is running. We build it with Ollama creates AgentBot F model file. Ollama processes the file and registers the new model. Let me run it to show the output. Our model is ready. Now look at the comparison. Ask the base model, who are you? And it gives a generic answer. Ask AgentBot at the same time what will give output. Let me show you in the next cell. So this is our AgentBot and this is the base model. We are asking the same question. Who are you and what are your rules? Look at the output. This is the base model response. So what is the output? It is telling that it is a generic answer, that I am Qwen and AI assistant created by Alibaba Cloud, and it's the primary goals. But when we ask to our AgentBot, it changes. It says I am an AgentBot and an AI assistant designed for the agentic AI from scratch series. My rules are the defined below, which is already defined in our previous codes. Here. Sorry. Here. So we can see that asking the same question, who are you? It's the first model, base model gives a generic answer, and asking AgentBot at the same question, it knows that it is an AgentBot. It knows its rules, knows it runs on Colab T4 GPU. All of that came from the model file. We did not pass a system prompt in the code at all. Now this is the streaming. Streaming is important for building any kind of real-time application. Instead of waiting for the full response to generate before displaying anything, you get each token and it's produced. Every day you use ChatGPT, Gemini, you see that the response is coming in a token of series in a continuous manner. And now your own chatbot will generate like this. The only change from cell 3 is setting stream to the true in the payload. Then instead of the response.json, we use response.iter lines, which gives us the JSON chunk per line as token arrive. Each chunk has a response field with the next token, sometimes a word, sometimes a part of word. We print it immediately with flash equal to true, which forces Python to display it without buffering. What's the output in the real time? You can see the output. It is like a ChatGPT. Is not it? See how tokens appear one by one. This is essentially now how ChatGPT's interface works. It is streaming tokens from the model. When the done field is in the chunk is true, generation is complete. At the end, we calculate tokens per second and tells how fast T4 is running your model. Typically 20 to 40 tokens per second for a 7 billion model on T4. Now the embeddings. Let me run the cell first. The last API feature is embedding. This is the foundation of RAG, Retrieval Augmented Generation, which is how you give the LLM access to your own documents. And embeddings take a piece of text and converts it into a vector, a list of hundreds of thousands of numbers. The key property is that semantically similar to the text produces similar vectors, meaning their vectors are close together in a mathematical space. We generate embeddings for 4 sentences, 2 about AI agents and LangGraph, 1 about Ollama, and 1 about pizza. Then we calculate cosine similarity between the pairs. Look at the similarity scores. Sentence 1 and 2, both about AI agents, scores around 0.9, which is very similar. Sentence 1 and 4, both about AI tools, scores may be at 0.85. Sentence 1 and pizza sentence, completely different topics, scores 0.7 or lower. This is exactly how a RAG system works. You embed your own documents, embed a user question, find the documents with the highest similarity score, and pass them into the LLM as context. We will build a full RAG pipeline in the later episodes. So the final summary, which is a quick notebook for you for using the complete Ollama. Ollama quick reference, which is a quick reference card of Ollama. Everything we covered today in one printout. You can back and check it anytime. Installation commands for all 3 platforms. All 8 CLI commands and their purpose. All 6 commands and the REST API endpoints and the quantization cheat sheet, the LangChain integration, the Modelfile template, and other necessary information. This is the complete Ollama picture. Next episode, we are using all of this to build a real AI agent with actual working tools. DuckDuckGo search, a file reader, and a Python code executor. All local, all free. If this was helpful, please leave a like. It helps to channel grow. Subscribe so you can catch episode 3 and drop any question in the comments. See you in the next one. Thank you so much.